forgot to start recording, so now we're actually going to start recording. So just to recapture, we're talking about the Denavit Hartenberg convention with an example of our Thormang robot and its kinematics and the motivation, even though in theory the coordinate system can be attached freely to the links. Some placements make the derivation of the kinematics easier than others. So Denavit Hartenberg convention allows us to describe the 4x4 transformation matrix with 12 unknowns using only 4 numbers. So let's have a look at what our transformation matrices actually look like. So the transformation from joint I to joint J is a 4x4 matrix that has a 3x3 rotation matrix. That is the relative orientation from I to J, as well as a translation vector of the origin from I to J, and then 0, 0, 0, 1 underneath, in order to pass through the constant for homogeneous coordinates. Now, the rotation matrix here is the 3x3 matrix, so that will correspond to 9 variables, 9 unknowns, but that is also a redundant representation. The rotation matrix actually is constructed by 3 rotations along the coordinate systems, so along the coordinate axis x, y, and z. Those are usually called the Euler angles, and then there's some problems with that because in order to derive the rotation matrix, you need to also fix a order in which you do the rotations, because if you have a coordinate system and you rotate around x, then y is in that, which is one popular way of describing the Euler angles, then you get a different result than if you rotate by y, then z, then x, for example. Or if you rotate first by y, then x, then that, you may also get a different result. So you need to fix the order of these 3 rotations the way that you want to do them. So that means even if we take into consideration that this 3x3 matrix here can be represented using 3 Euler angles, and then we have 3 unknowns in our translation here, that means now we have it reduced from 12 numbers to 6 numbers, which is an improvement, but Denavit Hartenberg goes even further, and it makes some more assumptions about the establishes some more conventions in order to simplify the derivation of the kinematics so that we can do it with just 4 numbers. And that's possible through a clever choice of the position of the coordinate frames as well as their relative orientation. So let's talk about the Denavit Hartenberg assumptions. The first assumption is the same that I did. That makes a lot of sense. You want to simplify modeling the effect of your actuators. So it makes sense to have a common way in which they act. And so we place the coordinate system in such a way that the z-axis aligns with the axis of actuation of the joint. So that means that for a rotational joint, the z-axis is pointing along the axis of rotation of our servo motor, and if it's a translational joint, then it points along the direction of the translation. So axis of actuation for a revolute joint is the axis that we rotate around. So that will mean that the joint variable theta I will rotate along the axis that is attached to link I minus 1, the z-axis that is attached to link I minus 1. And the axis of actuation of a prismatic joint is the axis that we translate along. And in that case, we have a joint variable di, which translates along zi minus 1. Now, secondly, when we look at the kinematics, then here on the Thormang, we have one link from this servo motor to this servo motor. And as far as the kinematics are concerned, the motion that we get when this link rotates, then this arm is going to rotate around the circle here. A circular path with respect to this joint here. But the actual shape of the link, like if we see here, we go up and then over, or if we go in a straight line, or if we have an even crazier link like this orange link here, the actual shape of the link doesn't matter as far as the kinematics are concerned here. So the only thing that matters is the displacement from this joint to that joint in a straight line, independently of what the actual link does. And then we can model this rotation here. And of course that also applies to all the further links that are attached. Like the end effector would also rotate around this point. And just as a reminder, the compound transformations, we go from the inertial frame, translate to the first location that we have, which would be the axis of our torso, and we aligned it. This is our inertial frame. And last time we said for humanoid robots, a common convention is it such that Z goes upwards, so the blue line goes up, X goes forwards, which then, in order to make this a right-handed coordinate system, we have to have the Y coordinate point to the left, right? Otherwise it's not a right-handed coordinate system. And then from there we can move to the first joint, which has joint 1 with the joint variable theta 1, and then in this case we align it with the z coordinate with our axis of rotation, so z will have to point this way, or it may point to the left, either to the right or to the left. That's up to us to decide, but that's here I chose pointing outwards, and then the other two frame axes we actually we could rotate around the z-axis here if we wanted to, but I aligned it in such a way that x remains forward and y points downwards. And for this joint here, then our axis is pointing outwards, z-axis is pointing outwards, and x and y are aligned in such a way that they're pointing upwards or to the left. In order to model the kinematics, we have to remembering that we need to right multiply our transformation matrices, because when we do the rotation, we actually rotate around this point and we rotate around this point, not around the origin. And if we left multiply rotating around this point, then it's the same thing as right multiplying the matrices. So that's the first Denavit-Hartenberg assumption. The first one is now for our transformation matrix. We know it looks like this. 12 unknowns, R11 to R33 and 014 to 024, 034. So 3 unknowns here, 9 unknowns here. Now the first assumption that Denavit-Hartenberg makes is that the x-axis, the next x-axis, and the previous z-axis, so axis xi plus 1 and zi, those two axes are perpendicular to each other. So here, this is actually what we have done previously as well. Z-axis, the previous z-axis is going upwards, the x-axis is going out of the page, so the previous z-axis and the next x-axis are perpendicular to each other. Similarly here, the previous z is going out this way and x is going up, so this and going up is also a 90-degree angle. Now, why is that interesting, or why does that make our life easier? Well, if the two vectors are perpendicular to each other, then that means that their dot product must be 0. Right? So that means that vector xi minus 1 multiplied by the next z-axis, the dot product between xi minus 1 and zi, that has to be equal to 0. Now xi minus 1 is r11, r21, and r31. Right? That's our previous x-axis. And the next, the x-axis here, the z-axis here is 0, 0, 1. So if I multiply them together, this must be 0. Otherwise, the two vectors are not perpendicular to each other. The dot product must be 0. So if we expand that, we get r11 multiplied by 0 plus r21 multiplied by 0 plus r31 must be equal to 0. Right? R11 multiplied by 0, R21 multiplied by 0, R31 multiplied by 1. We sum those up, that gives us the dot product. So that means that now we know that R31, this value here, must be equal to 0. So now we eliminated one of the unknowns in our rotation, in our transformation matrix. So we know this number is 0. Now we model the rotation. Since R31 is equal to 0, that means that there's no rotation around the y-axis, basically, because otherwise that would introduce a non-zero term here. So the relative offsets between frame I-1 and I, the relative orientation between frame I-1 and I is given, or can be described, using a rotation around Z by an angle theta, followed by a rotation along X by some angle alpha. And then we end up with, if we expand that, the two rotation matrices, we end up with this rotation matrix here. So the important thing is we still have the 0 term here. If we added another rotation along axis y, then we would get a non-zero entry here. So that means instead of using, and it makes sense, right? Because basically what we fixed is, if I know the two angles, theta and alpha, then because the third coordinate must be perpendicular, there is no more freedom in selecting that particular value. So with 2 rotation instead of 3 rotations, we can move from R-1 to R to transformation matrix, or to coordinate system I. From I-1 to I can get there by rotation around Z and X only. So here I implemented the same thing, just using SymPy, just to showcase that it's actually a very neat library that you can use in order to do symbolic computation in Python. So we define the rotation matrices, and then multiply them together. We end up with this rotation matrix here. So the second assumption is that we assume that Zi-1 and Xi intersect at each other. So not only are they perpendicular, but they also intersect at a point. So they can't be like this, but they actually have to intersect. So that means that the translation from I-1 to I is the translation from I-1 to I-1, the origin change, plus, and then since those two intersect, that means that I can move along my z-axis by some distance d, and then I follow along some distance a for my x-axis, next variable x, next x-axis. So the two intersect. So in order to go there, this is the Zi-1 axis, this is the x-axis, in order to go from here to there, I can get there by moving up until I hit the intersection point and then moving along X. So the expansion then is that from I minus 1 to I minus 1 that there's no displacement here. So that's 0. Then we get d multiplied by the z-axis, so 0, 0, 1 plus alpha, and then a plus a. And then this x-axis here, there's still a rotation along z, right? It can intersect, but I don't know which direction it moves off, but that's a rotation along z. So that would be along cosine of theta and sine theta, and no change in 0. So now we know we can represent the translation from coordinate system I minus 1 to I as a multiplied by the cosine theta and a multiplied by the sine theta, and then we have a displacement along z by d. So now we have two more unknowns that we introduced in our convention here. Two more numbers, a and d. And here we have the other two numbers, theta and alpha. And those four numbers are actually sufficient to now describe the kinematics of the robot system. So our transformation matrix from I minus 1 to I is now defined completely by these four numbers, which gives me, which we get by rotating around z by some angle theta. If we're dealing with a revolute joint, then this would be the actuation, right? Here's where we rotate the links. Then followed by translation along z by distance d. If we have a linear actuator, then this would be our actuation. Then this part here would be fixed, theta would be constant, and d would be a variable. If you have a servo motor, theta is a variable and d is a constant. So we translate along z by distance d, then we translate along x by distance a, and then we rotate around x by an angle alpha. And this is what I implemented here in my set of utility functions. Here I define the Denavit Hartenberg matrix with four numbers, theta, d, a, and alpha, and I return the matrix that I get from rotating z by theta, then translating along 0, 0, d, then translating along the x-axis, a, 0, 0, and then rotating around x by an angle alpha. So now if you don't want to calculate that, the Denavit Hartenberg convention, by generating 4 matrices and then calculating the dot product of those, the matrix multiplication, then of course you can also expand it and symbolically, and then you can generate this matrix in one step by calculating the corresponding products here and then generating your matrix. I think nowadays computers are fast enough that this doesn't, pre-calculating this in this form is probably not really necessary. You can also compound the 3 matrices that are constant for each link and then just have one with respect to your joint variable, either theta or d. If you're concerned about speed, that will be the only difference between calculating them one matrix at a time and then multiplying them together, or just generating the matrix in one go. This will be slightly faster, but given the speed of computation nowadays, I don't think that's a big concern, unless you have a microcontroller or something like that. Then this may be worthwhile. Also, for the computation, we should actually check out the computation, how much slower it is to calculate the transformation matrices, the forward kinematics, by using this form or even further expanding it and just calculating it one step at a time here. Like, I would argue that this format is probably maybe more efficient for the local cache, so it may not actually be slower at all. So now let's think about the interpretation of the Denavit-Hartenberg convention. So the joint angle theta is the angle between the previous x-axis and the next x-axis. Right? Because we have z, then we have an x-axis that intersects. We also have the previous x-axis, so the angle between those two is called theta. We call that angle theta. The link offset, the distance from OI minus 1 to the point where the two intersect, is d. The link length is the distance from the point of intersection to the new origin, or the distance between the two z coordinates measured along the x-axis, measured along the xi-axis. So this is our link length A, and then the link twist is the angle between zi minus 1 and zi measured in the plane around x, where we rotate around x. So how can we use that? Well, by assigning coordinate systems, assigning frames to the kinematics, we can start, well, we start with the inertial frame, frame 0, and then we iterate 1 to n, starting with the first joint up to the nth joint. So the axis can actually be, in theory, they could be assigned arbitrarily, but we assign them as the axis of actuation for the various joints. Once I have the z-axis defined, then we can set up the rest of the coordinate system. In particular, then we set up our inertial frame, and that inertial frame, since I have to get there from by going along z, that means that the inertial frame must lie somewhere on the axis that I defined for z0. Then we set up the other axis, x and y, x0 and y0, so the x and y axis of our inertial frame, in such a way that it makes sense for the system that we're dealing with, and that it forms a right-handed coordinate system. So now we have our inertial frame and our z-axis. So now we need to consider the three possibilities when assigning the axis for the other links. So if zi minus 1 and zi are not coplanar, then that means the one z-axis is like this, the other z-axis is like that. Now, if this is zi minus 1 and this is axis zi, I have to get there from zi by going along zi minus 1 and then following x, I, and they have to be at a 90-degree angle. That means that since xi also must be perpendicular to this axis, zi, because it's a coordinate system, right? So the xi, zi, and yi must be perpendicular to each other, all of them. That means if they're not in the same plane, if they're not coplanar, the only possibility I have for connecting those two would be with the shortest line, the normal between zi minus 1 and zi, and following along there. And that means we don't really have any choice. At that point, the origin, OI, must be where xi and zi intersect. And then yi can be assigned by just making it a right-handed coordinate system, making sure that it's a right-handed coordinate system. So if the two axes are not perpendicular to each other, are not coplanar, if they're not coplanar, then we have no possibility, there's no freedom left. There's only one choice for the x-axis, perpendicular to both z-axis, and that fixes the origin of the coordinate system OI, and then it means that the zi minus 1 and xi are then guaranteed to be to be perpendicular to each other, and I can get from I minus 1 to I by going along z and then going along x. And I go along z by distance d, and I go along x by distance a, two of the parameters of our Denavit Hartenberg formulation. Now, that's one case. The other case is that zi minus 1 and zi intersect. Right? So the two the two z-axes are not like that, but they actually intersect at some point. So if they intersect, since xi must be perpendicular to both of them, that means the only choice for xi now would be the normal to the plane established by zi minus 1 and zi. And that means that the origin is at that intersection point between the two z-axis, right? Because x must be perpendicular to those two. In this case, the xi can be assigned, must be perpendicular to this. So that means we have xi and zi, so then yi, we have no more degree of freedom. So we just assign it to make it a right-handed coordinate system. In that case, the amount that I need to travel from zi minus 1 along xi to get to zi must be 0. Right? The variable a for our Denavit-Hartenberg convention, if the two intersect, then that must be 0. And lastly, we have the case where zi minus 1 and zi are parallel to each other. Now in that case, xi can be anywhere along this plane, normal to zi minus 1 and zi. But I can shift it up and down. In this case, there's only one position where I can connect those two. The shortest distance between the two z-axis is well defined, but if they're parallel to each other, I can shift it up and down. So I can choose xi anywhere along zi, and in that case, the common convention, or what I want to do is change it so that xi is aligned with zi minus, with the coordinate system oi minus 1. So in that, then that simplifies my matrices, because now di is equal to 0. Alpha I, there will also be no twist along the x-axis at the end, so alpha I will be 0 as well. So the two alpha, that rotation is along x to bring zi minus 1 to align it with zi. But if the two of them are parallel, then there is no rotation between them. So that means that in this case, we set it so that di is equal to 0, and also alpha I will be equal to 0. So here's the Denavit-Hartenberg algorithm. We assign the z-axis as the axis of actuation for our robot. Then we assign the frames based on the position of the x-axis. Then we assign the y-axis to make it a right-hand coordinate system for each joint, for each frame. So then you can create a table that's called the Denavit-Hartenberg table, which just includes those 4 numbers: the joint angle theta, the link offset d, the link length a, and the link twist alpha. Then we can calculate the homogeneous transformation matrices for that. And then in order to solve the forward kinematics problem, we can simply then calculate the compound transformation matrix from 0 to n. So if we have a robot with turbo joints, then all our transformation matrices will be functions of theta. So A1 will depend on theta 1, A2 will depend on theta 2, AN will depend on theta n, and then we get the compound transformation matrix from our inertial frame to our end effector, our last joint n. And that's the description of the Denavit-Hartenberg convention. So for the rest of the class today, we would like to apply that and look at the differences between the Denavit-Hartenberg convention and how we defined the kinematics of the Thormang robot in the previous class. And then you'll sort of see why I don't follow the Denavit Hartenberg convention that closely. Can I hide this? Whoa. Pretty long line. So you can just hide them or collapse. Okay, not possible. So let's calculate the Denavit-Hartenberg convention for this upper body of the Thormang robot. And actually, I can just post a link here to the picture, and then we can easily swap without Now, if some of the numbers are missing in the description here, then just take your best guess. For example, the distance from here to there, that I think they actually give us the whole distance from what is that? From here to there. 569. That's the arms all the way stretched out. Okay. This one 424 millimeters, so half of that would be 212, and then this point here about 3/4, 2/3, so 212, so maybe 60 millimeters from the center to here. Things like that. Also, there's a servo motor placed below here in the hip, so we'll ignore that one. When we put the inertial frame at this location here in the groin of the robot, but now we just start with the upper body, the torso here. Or let's see if I so yeah. Okay, so I shall switch to here. And then, okay, here I get pixel coordinates. So now before we set that half, so from here (100) to there was the width of the torso. Oh no, from there to there was 212. So here from 100 to 454. Pixel coordinates. In the bottom left you can read the position of the cursor. So that will be 452. So then the distance per pixel So here the torso width was equal to 424. And that was to the first joint in the shoulder there. So that means the pixel in pixel what I have is here the x coordinate, if I get it reasonably close, is 98 for x, and here I get, if I center it on the circle, I get 452. So that will be 452 minus 98, but that's only half of the torso. So that will be multiplied by 2. So to convert from pixel to millimeters, it should be from pixel to millimeters. That will be divide. I want to multiply by that factor. So that should be torso width divided by torso width pixels. Let me just see. If that makes sense. 0.58. So yeah. And that's just because we don't have the physical robot there or the CAD specifications. To measure it ourselves. Zero 0.6. How come? If I round to 2 decimal places, why? Oh, 0. Weird. guess if I round it, just ends up 0.6. Okay, sure. So let's have a look at our DH algorithm and see what the first step is that we have to do. We need to assign the z-axis as axis of actuation for our servo motors. So now you can also do a screenshot and then draw in the z-axis that you want to assign. Probably easiest if you start with the joints first, assign the z-axis for the joints, and after that assign the z-axis for the inertial frame. And that is the same way that we did it previous class as well. First, of course, you have to identify the joints too, how many joints there are. We ignore the torso joint, we're past that already, so we have 1, 2, 3, 4, 5, 6, 7 joints in the left arm. The last one here is the gripper. So this would actually be a translational joint. We ignore that for now, so we only deal with the 6 servo motors. So take a screenshot, just like me, and then you can paint in the location of your z-axis. I suggest you use the blue color in order to draw in the z-axis. Because that's a common, another convention. Usually X is red, Z is blue, and Y is the green painted in. So by now you should be done. So here, let me just paint it in myself. And I need a smaller brush. Settings, spacing. Okay, pixel 3 by 3. So can I get pixel 5 by 5? Ah, not so bad. Oh, there used to be other options here. Close the tab. Okay. Ah, here. Yeah, this is the size. Yeah, okay, so that's better. I can make it a little bit bigger. And blue for our z-axis. So the first one is this joint here. So I'm gonna paint, oh, come. I'm gonna paint in right, so this will be the z-axis for our first joint. The second one would be here, pointing out of the page. The third one is here, pointing out of the page. First one will be here, fifth one is here, sixth one is here, and then seventh one would be the rotation would be stuck like this, but there's no actual rotation there at the gripper. That's only a translational joint, but that will be the next z-axis. So let's ignore that one for now. So here would be 1, 2, 3, 4, 5, 6 joints for our left arm. Now when I assign the coordinate systems, the z-axis, then we have X series or Pro series, doesn't matter. If you have a revolute joint, like a servo motor, then no, don't want you to zoom in. Yeah, okay. Here will be our servo motor. Now, as far as our z-axis are concerned, I have two possibilities, right? I can either have z go out to the right, or I can have z point to the left on this joint here. Here I can go out of the page or into the page. Out of the page, into the page. Right or left, up or down for z. And here into the page or out of the page. Now that choice I can make freely, but when you think about that we're dealing with the servo motor, the servo motors are always in the default of most servo motors. Even though you can often switch it in software, if you take it out of the box, and the default setting is usually that if you look at the servo horn with the motor, then the positive angle, the servo will rotate counterclockwise. That's just the convention that the builders have. So I like to assign the z coordinate in such a way that matches, because otherwise it's a little bit confusing if in your kinematics you move by -5 degrees and then you look at the servo joint rotating and it actually rotates in the other direction. You of course can compensate for that in software, but the less surprises you build into your kinematics, because it's hard enough to think about 3D for humans, the less surprises you build in, the less catastrophic failures you're gonna have with your robot. So here, for this particular joint, the horn is on the outside, is at this location, so I want Z pointing out for this point. Now those two here, the horn is in our direction, so I want them to point out of the page. Like in 3D, it would look like this a little bit. Here is the servo horn this way, so I want Z-axis to be located that way. Here, the horn is on the top, so Z-axis should be rotated this way, and here it's also mounted that way, so it should be pointing out of the page. So these are the Z-axis for our joints. Then how about the Z-axis of, if we look at the algorithm, for our inertial frame, now I just need to set up the coordinate system for the inertial frame. So here our inertial frame will be in the center of the torso. Make it here. And then for humanoid robots, like I already said, makes sense to talk about Z going upwards. And then now I have assigned all the Z coordinates. Right? Now I know where the Z coordinates go. And we can also then assign like we did previously, the Z-axis. We said X is pointing forward and Y is pointing to the left. right? So this would be our inertial frame. O 0. I want to move this one. Yeah. Now we have O 0. Right, so then we need to go through the algorithm and assign the remaining coordinates. The remaining coordinate axis. So in this case here, Z and Z0, Z1, they intersect. Say they intersect at the middle, which means that now we have no choice for our x-axis, because if you look at our assignment algorithm, if zi minus 1 and zi intersect, then xi must be the normal to those two coordinate systems. And that also fixes the origins of the coordinate system O1, and it then means that we can assign yi to make it a right-handed coordinate system. So according to the Denavit-Hartenberg convention, these two intersect at this point, so let's get a red color. I'm gonna pick that one. Okay. Here's the point where they intersect, and x has to be perpendicular to those. Now x can either point outside of the page or into the page. So let's no, don't move. Draw. Select none. So let's have x stay the same as previously. So now I have x, I have z, x, and z. So y must be pointing downwards in this case to make it a right-handed coordinate system. Like you have to x, y, z. That's how you can align the coordinate system. So I have x, I have z, and I'm looking at y pointing downwards then. So now y would be pointing downwards, and this would be the origin of our coordinate system O1. So O1 O1 would be here. In this case. So there's certainly nothing wrong with that, but you can see that the coordinate system that is responsible for this particular joint here is now in the center of the torso. The way that I assign the coordinate systems is always in such a way that the coordinate system is at the horn of the robot. And that is just so that when I print out coordinates of points in my robot system, then I can sort of have a quick look and I get an idea of where the robot is in 3D space. And even if that takes a little bit more computation or requires a bit, is not following the Denavit Hartenberg convention, I like it better that way. But yes, many people use Denavit Hartenberg very successfully. It certainly works. And if you're dealing in industrial settings, for example, then the industrial robots all use the DH convention because they have usually simpler kinematics than humanoid robots. And then they want to have the DH table if you want to implement kinematics or you want to discuss kinematics with them. They want to have exactly those 4 numbers. With humanoid robots, since I don't need to communicate the kinematics in such a way, usually I have a little bit more freedom, and I like to have the coordinates closely matched to where the position of the joints are, so that when I read off the coordinates, I get an idea of what the actual servo motor what the control is that the servo motor is currently sending, for example. That's why I also rotate around the z-axis an extra step often in order to align the coordinate system so that the joint angle 0 really means that it's in the home position for the robot. But here now we have aligned joint 1. So now you can try your hand on aligning joint 2. The Denavit Hartenberg parameters for inertial frame to joint 1 would then be that we go up along. First we need to rotate X. I don't need to rotate X. There we go. So we go up here, then we go up there, and there's no joint here now, so theta will be rotation by 90 degrees, so that the x-axis points in the right direction. And we go up, so it's this distance followed by that distance, followed by a, which is 0, because the coordinates system is exactly at this point, and then no rotation along the x-axis. So let's call that the left shoulder lateral joint, because it moves in the lateral plane. So no, wait a minute, I don't need to move it there, I just need to move it there. So I can go up along Z by this distance, and then I don't need to move along X, and then I can rotate around X by 90 degrees. Yes. Now let's take the measurement of that. If I look at the pixels, that will be D1. So when I measure this distance from here, that's 811, and that point here, which would be 335, 335, and what did I say, 811, 810, 810, and not 509, 509 and 810. So in pixels, we have this much, so D1, that's actually D0. The displacement along the inertial frame in millimeters is D0 pixels multiplied by pixels to millimeter. Yeah, round is not defined for some reason. I don't know why. Let me do this. Okay. So somehow my template expansion manages to mess up round. I have no idea why, so I need to specify it here. Okay. So here we have 180 millimeters, 18 centimeters from the bottom of the torso to the middle of this joint. Then theta is 0. Because I only need to rotate here. A is 0. And then alpha now I need to rotate around. So if I rotate around Z, then X moves to Y in the positive sense. So if I rotate around X, so I rotate around X, then it would move Y to Y in the positive sense. So we'll move this way. So now I have X, Z, this way if I rotate it that way. Okay. So it should be positive 90 degrees. Is that why? Yeah, no, I don't know. I don't know where the round comes from. The origin is at the point of intersection between Z0 and Z1. So that means D0 is equal to 0. So since the origin is at that point, that means that X is, I don't need to move along. So that means A is equal to 0. And now I get rotate x by 90 degrees. TH, T body, oh. Now I just need to get a theta. Theta D A and alpha theta 0 and we have D0 A0 and alpha 0. Of course you can put them in array too if you want to. Okay, let's see how that looks like. Yeah, theta, D, A, and alpha. Oh, and I guess these ones we can write in degrees. So here's our first Denavit Hartenberg parameter, and since I have it anywhere, I can make that table complete as we continue. So here's the table. So now you can work out from joint 1, which is O1, to joint 2. How do you model that? Using Denavit Hartenberg convention. Yeah, so now we go from O1 to this joint 1 here. That joint, that should be left shoulder frontal, because it actuates in the frontal plane mostly. Oh, okay. I hope I'm back. So I'll start taking some measurements. Now I have problems with round again. Ginger environment. Undefined doesn't define round. Oh, this is just not possible. My round. Okay. Equal to round value digit. And let's see if it's happy if I return this as a string. Type undefined. Okay, let me reboot the thing. Runtime, restart, runtime. And then let's run to here. No round is equal to round, I guess. No. Okay, run before. Okay, now let's hope this works. Okay, this works because I converted to a string. Okay. And then here So define the round part. No round. Okay, let's say this is a float and this is an int. That is really a weird problem. Now it's happy about that. But why can I not call that in my template then? D1. Yeah. It should be D1. Does that do it? Oh. Okay. So he has joined 1. Now I'm working on join 2. First I need to displace from the O1 to O2. Now O2, if we look at the position of the z-axis here, they are not coplanar, and that means that there's only one choice. The x-axis has to move from this z-axis to this z-axis and intercept it here. The origin of O2 must be at this position here then. So we're gonna go and get x. X can then either point downwards or point upwards. That doesn't really make any difference here, I guess. The only difference then would be if A is positive or negative. So let's make it point downwards. So then that means x axis will be pointing downwards. Let's try and get a straighter line. Right, so this would be our x-axis. Now I have x and z. So that means that y has to point to the right. So X, Y, and Z is pointing outwards, yes. And the distances that I need, first I need to translate along the previous Z-axis here from this point to this point here. I measured that was 454 pixels, and this is 97 pixels. And then I need to translate along X from here to there. So that would be, here we have 573, and here I have, put it there, 500. So 573 minus 500. Multiplied by pixel to millimeters. That will be A2. Then theta 2. So now we have to rotate. So X has to be pointing downwards. I have X. So that has to be point downwards. So that means I need to rotate it by X, Y, Z, and now I need it to rotate so that goes from X to Y. So that will be the positive direction, because X is supposed to point X, Y, Z. X is supposed to point downwards. So that means theta 2 is 90 degrees. And alpha 2 now, I have that Z pointing this way, so Z is X to Y, so this would be Y to Z is positive. Here we need to rotate around X now. So that should be negative. That should be X. Okay, yeah, should be negative. And I guess now we have join 2. Theta 2, D2, A2, and alpha 2. And now it also becomes apparent that it's pretty difficult to keep track of the coordinate systems in your head. So probably a good idea to start drawing some of the coordinate systems here. And Matplotlib does a really nice is a very nice tool to use in order to make that more easy to understand, more intuitive. So let's see. Now the coordinate system I can draw. I just need to see exactly what the arguments were that I wanted to apply there. Length, width, and then the possible translation matrix. Okay. Okay, so let's fix those. I don't know if that works. Let me see. restart. And run before. Make sure that all still works. Okay. So here's our inertial frame, Z going upward, y-axis to the left, x-axis going forward. And then let's calculate our Denavit Hartenberg coordinates. So A1 would be equal to DHH, the Denavit Hartenberg convention, and that would be theta 1 D1 A1 alpha 1. A1, or since it's the transformation matrix, I can just set it as A1 and then I keep plotting T. Here the rotation is actually not in the direction that I wanted. I wanted it to go outwards, so this has to be, our alpha rotation has to be negative. It's from Z to Y, not from Y to Z. So let's see, this here is negative. And then let's see what that looks like. X, Y. I don't know why Z. Okay, maybe make it thicker. God, Z is now so small. Ah, is the overlay? Because now my thing is 2 meters long, so let's make it 25 centimeters long. No, actually. It does. 175. Oh, it's the scaling, because this here is 5 millimeters, this is 5 millimeters, this is 175 millimeters, so the distance is going to be tiny, so the XY coordinates are going to disappear. So that's okay. That's going to work out. At the end, I only have 2 millimeters, so let's make it 2 millimeters. Let's make it 5 millimeters. Or I have 180, so actually I can make it 5 centimeters. And then at the beginning it's going to be looking a little bit weird, but other than that it's going to... So now we have our coordinate systems here. Now these ones just look longer because the aspect ratio is not the same. I can also set the aspect ratio to be equal. Let's see if that fixes it. That also makes it sometimes hard to see things. And it doesn't work in 3D. I think the aspect ratio now didn't actually change. Did I upload it? Yeah. Okay. Okay. So now we calculate A2, and that will be Denavit Hartenberg theta 2, D2, A2, and alpha 2. And our transformation then is T dot A2. And then we can plot the coordinate system. Join 2. Left shoulder frontal. Here is our inertial frame. And I wanted to make that one invalid syntax. Okay. I wanted to make that one a little bit longer. So let's make this one 10 centimeters, and the other one 5. So next we go to the left shoulder, that would be left elbow now. And that would also be frontal. Now this one is a little bit tricky, and you should certainly try that for yourself. Oh wait, I don't take this, I copy this one. So for joint 2, we move along Z as at the intersection, and then we rotate. So now from here, to here is one of the reasons. So one thing that I don't particularly like about the Denavit-Hartenberg convention is, for example, that the origin of this coordinate system here is actually quite far away from where the servo horn is, right? So I'd rather do a couple of more transformations to bring it there, and then when I print out the coordinates of this, the translation vector, then I can sort of guess where that is in 3D space, where that motor is located at this point in time. When I'm just doing debug outputs, it's much easier to visualize the thing. Here we have a similar problem. If we look at the z-axis, then we can see that from z2 to z3, we actually have parallel z-axis, right? They're actuating in the same plane, but they don't. They're parallel to each other. They don't intersect or but they are in the same plane. So that means that now for our, if we look at our Denavit Hartenberg algorithm, then we're looking at this third case here, zi minus 1 and zi are parallel to each other. Then we can choose xi anywhere we want. And the common way to do that is to align xi so that our displacement d becomes 0. Also, the z-axis are aligned with each other, so alpha I will be 0. So that means that here, if we look at this case here, that's a case that we're dealing with right now. Choose xi anywhere along zi, so we set it, we choose it so that di is equal to 0, which means that it's also again not at the servo horn. Alpha I will be 0 because the two z-axes are parallel to each other. So there's no rotation around x to align those two. So when we look at this case here, then we basically now, so now x has to connect those two, right? So we're dealing with this case. Two z-axis and x has to connect those two, and we set it so that d is equal to 0. So that means that now my z-axis has to go from this point to this point, right? And I need to do that with one single translation. So I need to actually calculate the distance here using the hypotenuse. If I get the coordinates of this joint and this joint. More importantly, I need to align the angle so that the angle theta is moving along this line here, not along this line. That would be perpendicular to the servo mounts or the link. So that's certainly doable. Nothing prevents us from doing that, but it means that instead of rotating here around z by 90 degrees, then going across and then going down, since I have to do it in one step, I need to rotate by x towards y. So I need to rotate by 90 degrees minus this angle here, minus this angle here. It's called a gamma. So that just doesn't match very well with the drawing of the robot. But certainly the kinematics, the solution is going to be correct. It's not going to cause any problem in that sense. So let's calculate that. Left shoulder frontal, and then here. So first, D3 is equal to 0. Then, and alpha 3 is going to be 0. just finish this part here. So Z3, X3, sorry, has to connect Z2 and Z3. So it intersects with both of them at a 90-degree angle. So we rotate around Z2 by 90 degrees minus the angle to the elbow. So let's have a look and see what that actually is. If I take the coordinates, the origin of 3 is going to be at this pixel location here. Which is 823, 619. 823, 619, 03x, 03y, and 02x, O2y is equal to, that was here. So that's 453, 573. 453, 573. So then dx that would be O3x minus O2x. And since the y coordinate is inverted, it will be O2x minus O3x, or minus O3x minus O2x. So then A3 is going to be the hypotenuse of delta x multiplied by pixel to millimeter, and delta y multiplied by pixel to millimeter. And that angle is going to be gamma. That angle is going to be math.a102 delta x. And actually, since I'm counting the angle negative here anyway, or it will be negative delta y here. So then the direction that I need to rotate for alpha theta, so that means theta 3 is equal to 90 degrees minus this angle gamma. So now I have A3, theta 3, D3 is equal to 0, and alpha 3 is equal to 0. So now I have all the Denavit Hartenberg parameters, so I can put them in. Because of course the coordinate system, the origin of this coordinate system is the point where x intersects, where x3 intersects with z3. So maybe I should draw those in a different color of red or different color altogether. Let's draw that orange. Let's say this one here and this one. This angle is gamma. But our x-axis has to be pointing this way then. Right? So it's not, in this case, that coordinate system must be, is not aligned with the world coordinate system. The axes are not, this is not pointing along either the x, y, or z axis of our inertial frame, which makes that also a little bit difficult to visualize. So in this case, I'd rather just break the Denavit-Hartenberg convention than having to think about that all the time. So let's see. Here we need to add our next joint. And then we can plot it. Theta 3, D3, A3, and alpha 3. Let's make sure that we have all of those now. Theta 3 is not defined. Negative 16 degrees. Yep. D is 0, A alpha is 0, and A is a distance of 313 millimeters. So then we can add that into our figure. Theta 3, D3, A3, alpha 3, T dot A3. And we plot the coordinate system. And I make that one a little bit thicker. So we'll see what it looks like. So now we have that. So this is a torso, this is a shoulder, this is the other shoulder, and this is moving down, but the scale is not the same. Like this is 400 here, 300 something. This is only 10 millimeters. So if you write that code and run it on your local workstation, then you can actually click on it and rotate the figure. Then it will be better. Or let me try and see if I can get a couple of snapshots. That would also work, I guess. See if that aligns it with 0 degrees, which should be ideally along X. No, I don't think that changed anything. And how come AX, AX? Oh. Here. Should be no row. Okay, so now we're looking at it from an elevation, maybe a little bit too high. .30 degrees, so let's make it 0 degrees. This is too far down, shouldn't be quite so far down. So that angle theta is wrong. Oh, because I don't have to rotate by 90 degrees, I just have to rotate by this angle. So that's... Oh no. That's what. It should be by 90 degrees to align the x-axis. X is now pointing down. I want it to move to the right, so I need to rotate by 90 degrees. It will go here. By 90 degrees minus gamma, it'll be pointing at this way. I just didn't convert it correctly to radians. "45 degrees. That can't be right. Yeah, no. I'm not sure why that happened. I want to set up the elevation a little bit high. I make it 10 degrees, 15 degrees. And this shouldn't be 45 degrees. This should be... Actually, let's see what delta x... Now I was worried about that. Because of the 4:3 aspect ratio. It should be y, not x here. Yeah, I'm not sure why I came up with a 45-degree angle there, but that's what I printed out, 370 degrees, negative 370. But then I noticed, and I had a mistake here, a bug here, there should be y, not x, of course. And let's see what the angle is that we get, minus 46. So now that should give us a better table. What does it say now? 7 degrees, so that's a more reasonable angle, except it shouldn't be positive. Oh no, it should be positive. Yeah. And let's plot it. I don't think that's correct. Theta 3 is 7 degrees now. Let's see what gamma is. Gamma is 82 degrees. And why does it print 7 then? Theta 3 is 90 degrees. Gamma is 82 degrees. No. Oh, that's because it counts from X to Y here. So there's no need to subtract 90 here. Okay, now this moved in this direction. And let's try and take a couple of angles, I guess. So let's enumerate some angles. I think the angles are actually in degrees. So let's take 0 degrees, 30 degrees, 60 degrees, 90 degrees. Azimuth. Now they're very small. So yeah, this translates in the wrong direction. Yeah. Okay, let's see if I can make it higher. It just doesn't scale that correctly. Let's take 10 degrees here. And 80 degrees here. And let's do it this way then. It's still too small. Fixed size is equal to 20, 10. let's make it 50. Okay, so that's a little bit better. And now if I go 1050, and switch this to 1.4. Okay, then they're a little bit bigger, and we can now see where the joints are a little bit easier. So this is 10 degrees, 30 degrees, 60 degrees, and 80 degrees view. And the joint is just moving in the wrong direction there. And that's because X, Y, Z, X, Y, Z. Yeah, it's pointing up, so that's correct. Oh, this one here, X is pointing backwards. So this is not the correct one that I wanted. So that means we need to fix A2. And now it's shifting out the way that I wanted to, and X is aligned here, as you can see. So now we've done inertial frame, joint 1, joint 2, joint 3. Joint 4 now is the same problem. The origin of joint 4 now, the same procedure, not the same problem. That means that it will be at the shortest path between this joint and that joint, which means instead of being at this location here where the actual servo is, that coordinate system is going to be placed here, with that going upwards and intersecting both this z-axis so that means we align here, and then y in or x, z, x, x and z. Oh my god. X and Z this way, so Y should be pointing forward. Okay, and now instead of translating from here to there, we really just translate from here along the x-axis. D is going to be 0. And then we need to rotate by 90 degrees to align the x-axis. So that's it as far as the Denavit Hartenberg convention is concerned. Now, next week, Monday, we will write the exam. The exam is going to be a virtual exam. Open book and open internet, and we will use the Discord server in order to administer the exam. The material that will be covered in the exam is everything that I covered in class during lectures, and I will post a sample midterm later this afternoon. Okay, good. Then that's the end of our class for today. I will see you next Monday. Bye-bye.